Hey, welcome. Today we're going to tackle a real powerhouse technique in calculus, integration by partial fractions. If you've ever just hit a wall looking at a super messy rational function, this explainer is for you. We're going to see how to turn these complex problems into a bunch of simple ones. All right, let's just jump right in. Take a look at this integral. At first glance, it's pretty intimidating, right? I mean, there's no obvious u substitution that's going to work, and it's definitely not one of your basic forms. Honestly, this is exactly the kind of problem where you just get stuck. But what if I told you the secret isn't some brand new complicated integration rule? The secret is actually algebra. Yep. It's all about taking this one big, messy fraction and strategically breaking it down into smaller, much friendlier pieces that, we already know how to integrate. And that brings us to the big idea behind this whole method. It is a classic divide and conquer strategy. We're going to decompose the problem, break it apart, before we even think about touching the calculus. So here's the formal name for it: partial fraction decomposition. We're taking a single rational function, which is really just a fancy way of saying a polynomial over another polynomial, your p of x over q of x, and we are rewriting it as a sum of simpler fractions. The whole goal, the entire point, is to get pieces that turn into simple things like natural logs or maybe an arctangent. Now, hold on. Before we go any further, here is the absolute golden rule. You cannot, I repeat, cannot use this technique unless the degree of the polynomial up top is strictly less than the degree of the one on the bottom. If it's not, you have to do polynomial long division first to fix it. Trust me, it's a super crucial first step that is so easy to forget. Okay, so let's say our fraction is ready to go. How do we actually break it down? Well, it turns out there are basically 4 standard scenarios you'll run into. Think of this as your toolkit. Once you know these 4 setups, you can handle pretty much any rational function they can throw at you. This table right here, this is our roadmap for the entire technique. It tells you exactly what your little baby fractions should look like, all based on the factors you find in your original denominator. So you'll notice how a simple linear factor just gets a constant a on top, but an unfactorable quadratic factor, that needs a full linear term, ax plus b. This chart is really the heart of the whole method. All right, let's make this real. We'll start with the simplest scenario, case 1. This is where the denominator factors into distinct, non-repeating linear terms. We're going to work through this example from start to finish. And to do it, we're going to follow a clear, repeatable 4-step process. Super simple. First, we factor the denominator. Second, we set up our partial fraction form. Third, we do a little algebra to find those unknown coefficients. And finally, the easy part, we integrate our new, simpler expression. Let's put this process into action. So first thing, we factor x squared minus 5x plus 6, and that gives us x minus 2 times x minus 3. Now, because these are distinct linear factors, our setup becomes a over x minus 2 plus b over x minus 3. Our whole job now is just to figure out what a and b are. And to do that, we start by clearing out those pesky denominators. We just multiply both sides of the equation by that whole x minus 2, x minus 3 thing. What that leaves us with is a much cleaner, much friendlier algebraic equation to solve. 1 equals a times x minus 3 plus b times x minus 2. Now, you could multiply everything out and match up coefficients, but there's a much faster way for these linear factors, and it's a really clever trick called strategic substitution. We're basically going to pick special values for x that make one of our terms just disappear. Just watch this. If we decide to let x equal 2, look at the b term. It becomes b times 0, and poof, it vanishes. We're just left with 1 equals a times 2 minus 3, which is just 1 equals negative a. So obviously, a has to be negative 1. See? Simple as that. So next, you guessed it, we choose a value to make the a term disappear. If we let x equal 3, that a term gets completely wiped out. We get 1 equals b times 3 minus 2, which just means b equals 1. And just like that, we're done with the algebra. So here's the payoff. This is the crucial point. Our original, kind of nasty integral has been completely transformed. It is now the integral of negative 1 over x minus 2 plus 1 over x minus 3. We have successfully divided and conquered the problem. And now, for the easy part, the actual integration. We know the integral of 1 over a linear term is just the natural log, right? So we get 2 natural log terms, one for each piece of our decomposed fraction. And hey, to put a nice little bow on it, we can use our logarithm rules. Remember that the log of a minus the log of b is the same as the log of a over b. This gives us our super clean final answer, the natural log of the absolute value of x minus 3 over x minus 2, and of course, don't forget your constant of integration, plus c. Excellent. So now that we've totally mastered the basic case, let's circle back to that challenge problem from the very beginning. This one's a little bit different, you see, because it involves an irreducible quadratic factor, which is our case 3. So what on earth is an irreducible quadratic? Well, it's just a quadratic term, like x squared plus 1, that you just can't factor any further using real numbers. It means the discriminant, b squared minus 4ac, is negative. And this type of factor needs a slightly different setup. And here it is, the pro tip. This is the single most common mistake people make with this case. When you have an irreducible quadratic on the bottom, its numerator isn't just a constant a. It has to be a full linear term in the form bx plus c. Please burn that into your brain. So, if we apply that rule to our problem, here is the correct setup. The linear factor, x minus 1, gets that simple constant a on top. But the irreducible quadratic, x squared plus 1, gets the full linear term, bx plus c on top. I'm telling you, getting this setup right is half the battle. Now, the algebra to find a, b, and c here is a little more involved. You'd usually use a mix of that strategic substitution trick and then expanding everything out and comparing the coefficients for x squared, x, and the constant. To keep us on track, I'll just tell you the results. A is 1, b is negative 1, and c is 1. And would you look at what happens to our integral now? That one impossible problem has split into 3 totally standard integrals. The first one is a simple natural log. The second is also a natural log. You can solve it with a quick u substitution. And the third? That's the classic form for arctangent. We've broken it down into textbook examples we know how to solve. So what started out as this really impossible-looking problem, it becomes completely manageable once you have the right framework. You now have the toolkit for partial fractions. So the real question is, what other integrals that once seemed impossible can you now go out and conquer?